one of the biggest payoffs to using normal distributions is that we can use them with certain other random variables that get too unwieldy to work with when the parameters are too large or when we have too large of a support. So in this video, we'll talk about how we can approximate binomial random variables using a normal distribution. And we have a theorem that tells us how we can do this and under what circumstances we're allowed to approximate a binomial distribution. So suppose we have a random variable which has a binomial distribution with parameters n and p. Remember that n is the number of trials and p is the probability of success in each of these trials. And it's so called because each trial is represents a binary variable. So yes, no, true, false, heads, tails, anything that can be modeled like that. And we do this repeatedly and independently. We're talking about a binomial distribution. So two conditions that we need to satisfy are, one, that our number of trials is greater than or equal to 20, and two, that both n times p and n times 1 minus p are at least 5. So remember that NP is n times the probability of success, which is actually the mean of x. Then x can be approximated by a normal distribution. I'll annotate here that we mean approximately, not exactly, because x is a discrete random variable and we're approximating it now with a continuous random variable. But it can be approximated by this normal distribution with a mean n times p, so the mean matches, and the standard deviation square root of np 1 minus p. These are the same mean and standard deviation of the original random variable, but we are just fitting now a bell curve to the probability mass diagram for a binomial distribution. So for example, suppose that we have a binomial distribution with 20 trials and a probability of success of 0.4. Now, 20 is right at the threshold of what we would consider for approximating using a normal distribution. So 1, n equals 20 is large enough. 2, n times p, which is 20 times 0.4, is 8. And n1 minus p is 20 times 0.6, which is 12. These are both larger than 5. So we're good to go on both counts. And if we were to fill out or draw the probability mass diagram, then we would see that the bell curve is actually a pretty good fit for this scenario. So how would we use this in practice? We actually began this chapter by looking at a random variable that represents the number of readings that test positive for sulfuric acid in readings of rainfall around a large urban center. In other words, out of a sample of rainfall, how many test positive for being acidic? So we found x being this number of readings where we had a binomial distribution with n equals 250 and p equals 0.23. And if we ask the question, what is the probability that 100 readings or more test positive in a random sample? We were actually asking the question about this binomial random variable, which, remember, this is a random variable that has a support of 251 discrete values from 0 to 250. So we're actually looking for the probability that x equals 100 plus the probability that x equals 101 all the way up to the probability that x equals 250. And each one of these is a binomial probability mass. So what we're actually saying is from k equals 100 to 250, we're going to add up all these probability mass function values, which is to say we're using the 1 minus the CDF of this random variable. And unfortunately, such a calculation would be extremely difficult to do by hand. I mean, really beyond the notion of reasonableness for anyone. And it even is daunting enough to cause a calculator to really spend some time on this. So this is unfeasible. We cannot do it this way. What we'll do instead is we'll approximate. We know, first of all, that n being 250 is way greater than 20. So that works out. 2, NP is 250 times 0.23, which is 57.5. That's greater than 5. And n times minus 1 minus p, by the way, just a hint, in case you haven't noticed, this value is always going to be 250 minus the NP that we already found. So this actually ends up being 192.5. That's also greater than 5. We're allowed to use the normal distribution. So in other words, x can be thought of as a normal distribution with mean mu being n times p, which is 57.5, and the standard deviation being n times p times 1 minus p all square rooted is approximately 6.654. And now we can use any technique we know with a normal distribution to find this probability. So namely, let's standardize. Our corresponding z-score for 100 would be 100 minus 57.5 all over 6.654. And when we simplify this, we get that this is 6.387. Now, before we even calculate, we should use our computational sense here. A standard normal distribution typically takes on values between -3 and 3. 6.387 is nowhere to be found on a standard normal cumulative area table. We would have to use a tech tool, or we would assert that this probability is exceedingly small, because what we're saying is that the probability of finding more or at least 100 readings that test positive in this sample is the same as or approximately the same as the probability that z, the standard normal distribution, takes on a value greater than or equal to 6.387. And that is vanishingly small. That is 0.00000000159. Or something along those lines. So this is just straight up 0. Because we will not go beyond 4 places beyond the decimal. We'll just call it 0, round. And for context, in case you want to know just how small this is on the order of the radius of an atom. So extremely unlikely.